There is a small planet so near the sun that it is scarcely visible in the bright glare of our star. Like an elusive ghost, it is best observed from Earth in the twilight hours, when the sun is gone from the sky. The ancient Romans gave it its name, Mercury. So little was known about the planet that scientists could only guess at its origin and evolution. The best photographs of Mercury added little to our knowledge. But when man learned to travel in space, the electronic cameras of a spacecraft called Mariner 10 revealed the planet in startling detail. In June of 1975, scientists from 5 nations assembled at the California Institute of Technology to exchange the information they had gained from the exploration of the planet Mercury by the spacecraft Mariner 10. Included in the group were scientists representing many techniques of exploration, including the detection of various forms of radiation, the study of gases in a planet's atmosphere, and the powerful scientific tool, photography of the surface of a planet.
Welcome to Pasadena. We are convened.
The photographic exploration of Mercury was led by Dr. Bruce Murray of the California Institute of Technology.
The objective I have is to present a relatively simple interpretation of the history of Mercury and to draw some conclusions about the other terrestrial planets.
The work that Dr. Murray and his colleagues are engrossed in goes beyond the exploration of a single planet, Mercury. They are seeking insights into the history of our entire inner solar system. The search for new information began with the launch of Mariner 10. After leaving the gravitational field of Earth, Mariner 10 began its long voyage to Mercury. The spacecraft's flight path was carefully chosen to skim past the planet orbiting between Earth and Mercury, cloud-covered Venus. The Mariner 10 cameras at close range were to show us a startling new Venus, a Venus we couldn't see from Earth.
Venus has been a real frustration to photograph from the ground because in the visible it's perfectly featureless. There is occasionally a little bit of indentation along the terminator, and occasionally one can see a little structure around the limb. But basically it appears from the Earth to be obscured by an incredible haze. In the ultraviolet, however, that's the wavelengths beyond the blue that the eye cannot see but photographic film can respond to. Very faint markings have been observed. And it was those faint markings in the ultraviolet that persuaded us to make a maximum effort to photograph Venus in the ultraviolet up close. The results of the Mariner 10 photography in the ultraviolet were really good. In fact, much, much better than we had hoped. Because, as you can see, looking at first a picture of Venus in the visible that was taken by Mariner 10, and then when we switched to one that was taken in the ultraviolet and has been enhanced with a computer to bring out the details, there's a tremendous pattern of organization of markings. The pattern of rotation of features on Venus in the upper atmosphere, way up high by our standards, is remarkable in that the atmosphere on Venus rotates faster than the surface. In the case of the Earth, the atmosphere tends to drag behind a little bit, as one might imagine. In the case of Venus, the atmosphere rotates all the way around the planet once every 4 days. The surface rotates once every 243 days. So the atmosphere is rotating almost 60 times as fast, at the top anyway, as the planet itself.
In August of 1990 to March of 1991, we revisited Venus with 1,852 orbits. After an absence of almost 20 years, the spacecraft Magellan removed the veil of Venus, and we see the surface for the first time. We begin with 3 craters in the Alpha Regio area. A new breakthrough with a scientific instrument called the SAR, or Synthetic Aperture Radar, enabled us for the first time to penetrate the thick veil of clouds that perpetually shield Venus. This heavy atmosphere of 97% carbon dioxide with a thin layer of sulfuric acid at the top captures and retains the heat of the sun, causing a greenhouse effect. The temperature on Venus is 470 degrees Celsius, or approximately 900 degrees Fahrenheit, a searing heat with crushing atmospheric pressure.
The gravitational field of Venus was used to bend the flight path of Mariner 10 inwards towards Mercury. Then the gravity of the Sun pulled Mariner towards its first encounter with the planet. "5 billion years ago, a vast cloud of gas and dust floated through the galaxy we call the Milky Way, the ghostly remains of a great star that had died in a gigantic explosion. The gas and dust is twisted and shaped by magnetic forces, electrical currents, and the subtle pull of gravity. As it swirls around a thickening core, the huge cloud gradually flattens into a disk. Dust and gas gravitate slowly inwards, and eddies begin to form in the cloud. Particles of matter cluster into solid bodies. The larger bodies continue to grow, sweeping up particles and dust as they orbit the condensing core of the disk and begin to heat under the increasing gravitational pressures. In the central core of the disk, incredible heat is being generated, hotter and hotter, until it reaches critical temperatures. And then, billions of years ago, a nuclear reaction occurred, and our sun was ignited. Its intense radiation repels the surrounding gas and dust. The increasing heat of the inner planets has formed them into molten spheres. Mercury, like the other inner planets, is continuously bombarded by debris that form craters on its surface. In the final stages of its formation, Mercury glowed from internal heat. Hot lava was forced to a surface being torn by collisions with masses of rock that were shaping the planet. The same heat that triggered the lava flows also melted rock and metals in the interior of Mercury. Heavy iron concentrated at Mercury's center to form a dense core, which was overlain by a thin shell of lighter material brought to the surface by lava flows. Again, the surface was gouged and pitted by a great series of impacts, leaving huge craters on the surface. The Mariner 10 photographs have revealed these early craters to scientists for the first time. One of these craters was formed by a massive rock, perhaps a small planet that crashed into Mercury. In the Mariner 10 photographs, half of this huge crater was hidden on the night side of the planet. Today, this huge crater is called Colorus. The impact spewed millions of tons of debris across the surface of Mercury, creating a ring of mountain ranges over a mile high. The floor of this basin was split by great surface cracks, wide and deep. As this surface continued to form, deep inside Mercury, its heavy iron core began to contract. The surface buckled, cracked, and great sections, hundreds of miles wide, were split open, leaving immense mile-high walls of rock called scarps. Again, there was a great flow of lava covering many of the large craters and leaving smooth, flat plains. This set the stage for the final episode in the history of Mercury, a period of light cratering of the Great Plains. In this time, Mercury died. The internal heat that triggered many of the events in the planet's history turned off. And for 3.5 billion years, Mercury has remained as we see it today.
Before Mariner 10, there were a multitude of possible Mercuries. Now there's only one, the Mercury of craters and basins and plains. And this illustrates how photography can be an exploratory tool. It displays features which were perhaps never even anticipated and then sometimes could not even be imagined before the experiment was flown. In a sense, it provides answers to questions that were not even asked. This was true at Mars when Mariner 4 returned pictures of what appeared to be a moon-like surface. It had been expected that Mars might be very much like the Earth, with folded mountain ranges and many other Earth-like features. Instead, it looked like the moon, and that was a big shock. And it was an even bigger shock when Mariner 9 in 1971 visited Mars again and found huge volcanoes and even some peculiar sinuous channels that looked like they might have been formed by flowing water at some point in Mars's history. Now Viking has transported man's vision to the actual surface. The fantasy of science fiction has been replaced by the strange, lonely reality of the Martian landscape. When Mariner 10 flew by Venus, it discovered an unexpectedly well-organized set of cloud motions. And the unexpected was certainly encountered in the case of Mercury, which turned out to exhibit not only moon-like features on its surface, but a sequence of events there that seemed to be very similar to those of the moon. And that's extraordinary, because Mercury is very different inside compared to the moon. And that means it must have had a different history of heating and modification of the surface from the inside. And furthermore, it lives in a very different part of the solar system, much closer to the sun. And therefore, it must have experienced a different exterior history as well. And yet, the pictures show that Mercury has a surface history very similar to that of the moon. And to me, that's extraordinary.
A comparison of the craters on the Moon, Mercury, and Mars shows that these inner planets were subjected to cratering at the same time. Before Mariner 10, it was believed that the source of cratering of the inner solar system was the asteroid belt orbiting beyond Mars. Because of the difference in distance from the belt, it was assumed that no two planets would be cratered the same. Those planets farther from the asteroid belt, like Mercury, would have fewer craters. But a careful count of the craters on Mercury and a comparison with those on the Moon and Mars showed them all to be roughly equal. If the crater count is equal, then the source could not be the asteroid belt, but must have come from elsewhere in the solar system. One strong possibility is the planet Jupiter, with a gravitational attraction second only to the Sun. It is possible that on 2 occasions, Jupiter literally hurled millions of tons of rock inwards towards the Sun to impact the planets of the inner solar system, including Mercury. This cratered record on Mercury was read 3 times because of a fortunate coincidence. Mercury's orbit around the Sun is 88 Earth days. Mariner 10's orbit was twice as long, or 176 days. These synchronous orbits allowed Mariner 10 to fly past Mercury a second and third time. The path of the first flyby was on the dark side of Mercury. The second encounter sent the spacecraft past the light side of the planet specifically for photography. After another 6-month journey around the Sun, Mariner 10 made its third and final encounter to look again at a major discovery made during the first flyby: the presence of a magnetic field around Mercury, similar to Earth. A bow shock wave blocks the solar wind from the Sun and deflects it around the planet, creating an environment similar to the magnetic field around Earth. This discovery was a surprise because Mercury's slow rotation, about once every 57 Earth days, had led scientists to believe that the planet could not generate a magnetic field. It is believed that Earth's magnetic field is generated by an interaction between the planet's faster rotation and its molten core. Mariner 10's discovery may change theories on how these fields are formed, and has given scientists their first opportunity to compare 2 magnetic fields in the inner solar system. There were other measurements made at Mercury by Mariner 10. Infrared showed that Mercury's surface ranges in temperature from 700 degrees Fahrenheit to 300 degrees below zero, the widest temperature range of any planet. The ultraviolet experiment revealed that Mercury has a very thin atmosphere of helium. Sensors measured the invisible cosmic rays which flood our solar system at tremendous speeds, penetrate any surface, and are unaffected by gravitational forces. Their source is unknown.
Exploration is an adaptive process. Each new piece of information adds to the value of others that were accumulated earlier. We had the results of the Apollo program on the Moon to help us understand the timescales and to some extent the processes we were seeing when we looked at Mars with Mariner 9. Now that Mariner 10 has looked at Mercury, we can begin to compare it with the Moon and Mars and begin to realize that there is a common solar system history which has been recorded on these planets, whose early surfaces have not been erased by erosion and other atmospheric processes. That same common history affected the Earth too. And so by looking at these surfaces, reading those records, we're in fact looking back into the Earth's history, into a heretofore unexplored domain of time, our own history on the Earth. Now we can begin to compare and contrast, to look for similarities and differences, and try to recognize our family relationships among the terrestrial planets. Are we cousins or brothers, or are all of us bizarre strangers that happen to inhabit the same portion of the solar system? That's the task of comparative planetology. That's where we go from here.
Of all the planets in the solar system, Earth and Mars, the third and fourth planets from the Sun, are the most similar. But despite the similarities, Mars is essentially like no other planet. It is a unique world. It was an elusive and baffling planet to astronomers for hundreds of years. Through early telescopes, it appeared to be a small red sphere, later estimated to be about half the size of Earth. One of the earliest known representations of the planet, drawn in 1659, indicated markings on the surface, and by the movement of these dark patches across the disk, it was shown that Mars rotated on its axis in a period only a little longer than Earth's, about 24½ hours. It was observed, too, that the tilt of its axis, like the Earth's, exposes its polar regions alternately to the sunlight. Thus, each hemisphere has a summer and winter period. And since Mars orbits the Sun in 687 Earth days, one Martian year in each of its seasons is almost twice as long as Earth's. Later mappings of the planet displayed light and dark regions identified erroneously as continents and oceans. The land masses red as the sandstone districts on Earth, the water a greenish blue. In 1877, an Italian astronomer, Giovanni Schiaparelli, discovered what he called canali, or channels, resembling, he said, the finest threads of a spider's web drawn across the disk. In America, Percival Lowell founded an observatory to study these Martian features. Massive irrigation systems, he called them, designed to carry water from the melting ice caps to the major centers of a dying civilization. Science fiction writers populated the cities with terrible creatures of heroic size, with skills beyond Earthman's dreams. In the 1960s, 3 Mariner spacecraft flew by Mars and photographed about 10% of the surface. Gone were the canals, gone were the cities, gone the brilliant and sinister Martians. The photographs revealed a cratered landscape much like the Moon, waterless and apparently hostile to life. But in 1971, the Mariner 9 spacecraft orbited Mars and transmitted more than 7,000 photographs of the planet to Earth. The extensive mapping revealed a new and unexpected world. The southern hemisphere, seen by earlier spacecraft, flattened and gouged by the impact of meteorites. The northern hemisphere, a vast plain with few craters. And rising from the plain, a great dome called Tharsis, topped by giant volcanoes. The plateau that joins the two hemispheres is cut by a vast and deep canyon, and by channels with the characteristic patterns of stream beds on Earth. Some of the channels suggested that water may once have flowed on Mars, and thus life might have evolved and possibly adapted to Mars' changing conditions. And then in 1975, 2 Viking spacecraft were launched, each of which was programmed to land a robot on the Martian surface. One of its principal objectives was to test for the presence or absence of living organisms. A communication system linked the spacecraft to the Mission Control and Computing Center in Pasadena, California. On June 19, 1976, the first Viking arrived in the vicinity of Mars after a year-long journey of more than 400 million miles. Once in orbit, its cameras were turned to a detailed examination of the landing area. Imaging teams on Earth scanned some 800 photographs covering a territory about the size of Texas. The chosen landing site was a flat expanse with a few impact craters, one of the lowest regions on the surface. On July 20th, 1976, flight controllers ordered the lander to separate from the orbiter.
5, 4, 3, 2, 1, separation. Descent sequencing, we're at mission event word 0, and we have DL separation.
Because of Mars' great distance from Earth, the signal traveling at the speed of light, 186,000 miles per second, took 19 minutes to reach the spacecraft. This necessitated a completely automated system on board for carrying out the landing maneuver. During the lander's descent, its instruments analyzed the properties of the thin Martian atmosphere.
9,000 feet coming up on quarter bar, please.
Good roll attitude hold.
Pretty close to quarter bar. Firm quarter bar. Two loops and a high. Got it. We have quarter bar.
Lander confirmed parachute deployed.
Recon 1, TM2. Drive sync.
UHF minus 105.1.
Format 3 is in sync.
All right.
Format 3 is sync.
Leg deployed. 4,800 feet, 177 feet per second. Confirm roll maneuver.
Parachute separation.
Roger. Minus 105. 23 Gs. 2,600 feet, 188 feet per second.
2,600 feet. 2,600 feet.
366 feet.
73 feet per second.
ACS is close to vertical. Nav is green for touchdown. ACS is green, 1.5 degrees per second max, 0.2 Gs. Feet per second.
Touchdown win. Fantastic. 16 kilobits confirmed. Yes, we have a touchdown time of 12 hours, 12 minutes, 07.1 seconds.
A job very well done. Outstanding, great, navigation perfect. I'm assuming that we must be sitting right on the X. So that's the smooth area. So everybody just did fabulous and couldn't be more pleased. Thank you.
25 seconds after landing, one of the 2 cameras was initiated and scanned the first picture of the Martian surface.
About a half an hour later, when it started to come back from the orbiter, and we got the first 7 lines on the TV monitors, you could see gray and white light levels, and we knew there was something there. Look at the beautiful rock. Fantastic. And all of a sudden, we were looking at the surface of Mars, and it was clear, it wasn't dusty, it was sharp. And when we got to the end of that first picture, with the dust and small pebbles in the footpad, it was just, it was really a miracle.
In an instant, the picture was wiped off the TV monitors, and behind it came the filling in of the second picture, a long panoramic view that covers 300 degrees and extends from the lander to the horizon. It disclosed a sector of the basin called Planitia, covered with sand or dust and littered with rocks.
The following day, Viking sent back the first color picture. A fine dust, red or yellow-brown, covers the ground. The sky is a light tint of the same color due to the particles of dust suspended in the air. 45 days after these historic events, Viking 2 landed in an area 4,600 miles northwest of Viking 1's landing site. A vast plain, littered too with rocks resembling those on Earth, produced by volcanic processes or by meteorite impact. While the landers conducted experiments on the surface, the orbiters swinging around the planet measured variations in moisture and temperature and took high-resolution photographs of the Martian terrain. In the formation of a planet, heat is released and remains embedded in the growing mass. Because the heat can't escape as rapidly as the mass is growing, a point is reached eventually where the interior melts. On Mars, the heavier material sank toward the center, and the lighter material rose to form a crust at the surface. And this crust contained ice and other condensates. A later stage may have occurred where molten rock intruded into the crust and melted the ice, causing a slurry of water and rock and dust to flow across the surface. Some observers believe that such a process may have been the cause of the major channels which we see on the surface of Mars today. But others believe that in Mars' first billion years, the atmosphere may have been warm and dense enough for rain to fall and for rivers to flow. Gradually, the original thick, wet, and warm blanket of the atmosphere evolved into the thin, dry carbon dioxide atmosphere we find there today. Because of Mars' low atmospheric pressure and low temperatures, water can't exist in liquid form. It must either freeze or evaporate. But while there are no oceans or rivers on Mars, there is more water in total than anyone had expected. The residual polar cap in the north, which remains after the hottest part of the northern summer, is water ice mixed with dust. And the measurements of the seasonal behavior of water vapor over the planet suggest that there is a vast reservoir of ice beneath the surface, so that one can think of the residual polar cap as the tip of an iceberg protruding from a sea of rock. At lower latitudes, the water vapor condenses to form clouds that ride high in the atmosphere or swirl around the slopes of Martian volcanoes. And further south, in the canyons and valleys, there is frequently an ice haze seen to form and evaporate in the early hours of the morning as the sun warms the atmosphere. On Earth, the ocean's heat and moisture and the heat and air currents over land masses interact to produce complex weather patterns. On Mars, because of the absence of large bodies of water and of massive cloud covers, the weather doesn't vary much from day to day. Like a remote weather station on Earth, Viking's meteorology instrument measures Mars' atmospheric pressure, temperature, wind speed, and wind direction. Temperatures range from minus 122 degrees Fahrenheit just after dawn to minus 22 degrees in the mid-afternoon. Light winds from the east in the late afternoon change to light winds from the southwest after midnight. Maximum wind speed is 15 miles per hour. But in the early summer, the heating of dust particles in the air generates violent dust storms in the low regions of the planet. Driven by winds that reach 150 miles an hour, they may blanket the entire planet in a few days.
In order to understand the geology and physics of wind-blown particles on Mars, we're conducting a series of experiments using this this enormous space environment chamber here at NASA's Ames Research Center. We've placed an open circuit wind tunnel in this chamber, and we're able to operate at atmospheric surface pressures comparable to those on Mars. In this particular series of experiments, we have placed a crater model in the tunnel floor, and we want to determine the zones of erosion and deposition around the crater. In this particular case, we're going to let the wind blow across the crater and see what those zones of erosion and deposition are like.
The light and dark streaks associated with craters are the most common features on the surface of Mars related to wind. The light streaks are deposits of fallout from the global dust storms. The dark streaks are regions from which a thin layer of light material has been removed, revealing a darker underlying surface. These streaks serve as wind markers. Their patterns define the wind flow. To the geologist, the features seen in the tens of thousands of photographs transmitted by Viking are the visible signs of the enormous forces and processes that have shaped the surface of Mars. The excavation of large basins and craters by the impact of meteorites and asteroids. The raising of mountains by the action of volcanoes. The faulting and subsidence of the crust as the planet expanded. And the cutting of channels by water, or abrasive particles driven by winds over a period of tens of millions of years. The key to the age and sequence of these features is found in the number and condition of craters. Those areas with fewest craters are assumed to be the youngest. Here, a fresh crater overlies an ancient eroded one. Here, the rim of a crater is eroded by water or wind. And here, adjacent to a fresh crater, is one of a cluster of crater rings, craters that have been buried to varying depths. Over millions of years, the repeated flows of lava built the volcanic mountains of Mars. 12 are larger than any on Earth. The largest, Olympus Mons, rises 3 times higher than Mount Everest and is broad enough to cover the whole chain of volcanoes that form the Hawaiian Islands. The great gash that cuts through Mars' equatorial zone is Valles Marineris, a mighty canyon system that extends over an area more than 3,000 miles long and up to 400 miles wide, and drops 4 miles below the flat cratered surface of the plateau. Canyon walls are gullied, dissected by tributary canyons, or scarred by catastrophic landslides, leaving steep cliffs and great fractured surfaces. Extending for 30 miles on the canyon floor is a field of sand dunes, suggesting that some of the debris produced by the collapse of the canyon walls was removed by wind. These ancient channels that resemble dry riverbeds on Earth could have been formed by primeval rainstorms. But the vast channel systems that start in areas of collapsed terrain, with broad streamlines extending hundreds of miles across the lowlands, and teardrop-shaped islands soaring to thousands of feet above the channel bed, testify to a process without any parallel on Earth. Viking also photographed the 2 cratered moons of Mars, Phobos, the inner moon, marked by striations which, on closer view, resolve into grooves several miles long, and Deimos, the smaller outer moon. Viking, traveling at 3,800 miles an hour and passing only 30 miles away, could observe boulders on the moon's surface, some as large as 100 feet across. The geologic record of the planet suggests that Mars, like the Earth, has experienced periodic changes of climate. The best evidence of this is seen in the strange spiral patterns of Mars' polar regions. The dark bands are scarps or cliffs of bare ground within the North Polar ice cap. On each scarp are numerous small terraces eroded from layered rocks. This is a model of layered terrain, an area about 40 miles across. It is believed that the large scarps and the small terraces represent two different cycles of climatic change which occur simultaneously. Because of Mars' oscillation in its orbit about the sun, the polar regions are alternately warm and cold for periods of tens of thousands to millions of years. During the cold period, mixtures of dust and ice were deposited in a series of near horizontal layers, obscuring the underlying topography. Then a period of warmer climate followed, and erosion set in, cutting deep valleys into the icy mass of the polar caps. After the erosion cycle, new layers were laid down, and another episode of erosion followed. This oblique truncating of one set of terraces by another indicates that the climate turns on and off, the first geological evidence for cyclical climatic change on a planet other than the Earth. The speculations about changes in the atmosphere and climate were closely related to the notion that life in some form might exist on Mars. On Earth, life developed several billion years ago, at a time when the overall properties of Mars and the Earth were very similar.
Now, over the ensuing billions of years, Mars and the Earth evolved separately. However, Mars today still has chemicals on its surface, an atmosphere, temperatures and pressures within which we believe life can exist. The Viking lander was equipped with 3 life detection experiments designed to test for chemical changes caused by life processes that are familiar to us on Earth. On Earth, all living organisms interact with the environment through a process called metabolism.
Animals, for example, take oxygen from the environment and use it to combust food, thereby obtaining energy. At the same time, they release carbon dioxide and other waste products into the environment. Green plants and some microorganisms do the reverse in the process of photosynthesis. They remove carbon dioxide from the environment, and using sunlight as the energy source, they convert the carbon dioxide into organic matter and release oxygen into the environment.
If the experiments on Mars indicated that similar processes were occurring, then we would presume the possible existence of organisms on that planet. Well, our results on Mars in certain experiments gave us data that seemed to mimic the metabolism of living organisms. However, careful analysis of that data indicates that it is probably the result of chemical rather than biological processes.
On Earth, all biological systems are based on organic chemistry, and it was believed that life on Mars would also be based on organic compounds. The notion was strengthened when experiments on Earth demonstrated that organic materials can be formed under simulated Martian conditions.
We used finely powdered minerals like those expected on the Martian surface. Then we added traces of water vapor and radioactive carbon monoxide at low pressure. To simulate Martian sunlight, we irradiated the mixture with light from a xenon arc lamp. When we heated the sample and captured the gases that were formed, our radiation counter showed that the carbon monoxide and water had been converted to organic compounds.
But Viking's instruments failed to detect organic compounds of any kind. That fact, in the opinion of some observers, has increased the odds against the existence of living organisms on Mars.
If we were able to do 1,000 experiments, different experiments on Mars, and to do these in a wide variety of places on Mars, in the canyons, on the polar caps, in some deep areas of the surface, and if in all of these experiments we got negative results, then the answer to the question, is there life on Mars, would almost certainly be no. But on the basis of just a few experiments, done at only 2 sites, very bland sites on the planet, I think it would be unscientific for us to come to that conclusion. All we can really say, for sure, is that we have run across some very interesting chemistry, a kind of chemistry that we do not see in surface samples from the Earth or surface samples from the Moon, and that's about where we are at the moment. Today, in laboratories across the nation, scientists are trying to simulate the results that we obtained on Mars. Some of the scientists are concentrating on irradiation experiments to see whether solar energy acting on Mars could have produced chemicals to account for the results. Other experiments are assuming that these chemicals were there and are testing one or another of these chemicals to see whether they can account for the results that were obtained.
The question of life on Mars is only one of the inexhaustible number of questions for which we continue to seek answers in space. Questions about the origin and evolution of the solar system, of our own planet, and our own species.
The Voyager team of engineers and scientists spent 7 years designing and planning for the exploration of Jupiter and Saturn. The spacecraft are endowed with intricate logic systems and, when necessary, can make their own decisions without contact from Earth. They carry instruments for 11 science investigations of the outer planets and their moons. The radio link with Earth is channeled through a large dish-shaped antenna that dominates the spacecraft. 2 television cameras are the eyes of the spacecraft. They can be aimed with great precision. These instruments detect the unseen forces that swirl around these distant worlds.
Planetary astronomer Dr. Bradford A. Smith from the University of Arizona is imaging team leader for the Voyager mission to the planets.
It's particularly exciting because we're really going into the unknown. I think this is the first time since Mariner 4 that we were less prepared for what we have finally seen, in that we knew essentially nothing about the surface properties of the Galilean satellites. We knew very, very little about the sort of detail and dynamics that we'd be seeing in the Jovian atmosphere. So it was really a first look, and a very, very good first look at that. And that always makes a mission exciting.
September 18th, 1977. Voyager is 7 million miles from Earth. Its cameras turn back to record the blue Earth and crescent moon together in a haunting photograph of our home in the solar system. 14 months later, Voyager 1's cameras transmit the first photographs of Jupiter. February 5th, 1979. From a distance of more than 17 million miles, Jupiter and 3 of its moons are caught in a single frame. At 12 million miles, Jupiter's clouds of gases and ice particles are seen to swirl and twist in strange new patterns invisible from Earth. From a series of more than 4,000 photographs, a time-lapse movie is made that covers 10 Jovian days. The atmosphere is more complex than had been thought.
Jupiter is, first of all, a large ball of gas. It may, at its center, have a silicate core. That core may be surrounded by metallic or liquid hydrogen. But once one gets away from that inner core, which Voyager certainly cannot observe, we have a gaseous atmosphere. What Voyager is able to see is the very top of that atmosphere where the clouds form, the so-called tropopause. And we may be seeing individual layers of clouds, the highest most being composed of crystals of ammonia, that is ammonia ice, and these clouds are analogous to the high cirrus clouds that form in the Earth's atmosphere.
Last March, as Voyager 1 arced past Jupiter on its way to Saturn, its cameras recorded pictures of the 4 largest satellites, or moons, that orbit the huge Jovian planet: Io, Europa, Ganymede, and Callisto.
Europa, the size of our moon, resembles a cracked billiard ball. But the complex markings are curiously flat, like stripes painted on the surface. Its icy crust is thought to float on an ocean melted by interior heat. Io is the most spectacular of the Jovian moons. Its vivid, mottled surface with oddly shaped blotches of color mystify the scientists. Surely the strangest object ever seen in our solar system. Ganymede is as large as the planet Mercury. Its dark, ancient terrain is spotted with white impact scars. Adjacent areas are cut by jumbled patterns of grooves and ridges. Callisto is the outermost of the 4 large moons. Every inch of its surface bears the scars of billions of years of cratering. Two scientific discoveries occur during the first flyby of Jupiter. On March 4th, 1979, Voyager 1's cameras photograph a faint ring of particles surrounding Jupiter. Several months later, Voyager 2 photographs the dark side of Jupiter. Backlighting by the sun produces a spectacular view of the ring. It is ribbon-like, 3,600 miles wide. Jupiter now joins Saturn and Uranus to become the 3rd planet known to possess a ring system. A second discovery solves the mysteries of Io's bizarre surface. On March 8, 1979, Voyager 1 takes a remarkable photograph of Io. During a routine study of optical navigation, an engineer sees what at first appears to be a crescent cloud. Scientists soon realize that it can only be a volcanic plume erupting from Io, a huge fountain of molten sulfur, gas, and bits of rock surging upward against the moon's weak gravity. A re-examination of Io photographs reveals other active volcanoes, the first seen beyond Earth. Jupiter has a huge magnetic field. The field would expand symmetrically in all directions if it were not impacted by the solar wind, a streaming flow of particles from the sun. A bow shock is created where the solar wind meets the magnetic field. Behind the bow shock, the field is warped and turned inward upon itself by the pressure of the wind. It is formed into a long tail that extends 500 million miles to the orbit of Saturn. As Io moves in its orbit around Jupiter, it creates a unique relationship with the planet's magnetic field. In this polar view, Jupiter, spinning on its axis every 10.5 hours, drags its magnetic field and trapped radiation with it. But Io's orbit is slower, 43 hours. As a result, clouds of trapped radiation in the magnetic field sweep past Io and strip away 1 ton of sulfur and oxygen atoms each second into space. These atoms form a torus, a huge ring of electrically charged particles trapped by the magnetic field. An electrical current of 3 million amperes flows along magnetic field lines linking moon and planet. Torus material flattens the magnetic field and flows away from Jupiter to create the current sheet, a thin sheet of charged particles which distorts the field near the magnetic equator. The Voyager scientists had been saturated with surprises at Jupiter, and they approached Saturn with cautious, open minds. In this computer-generated film, Voyager is shown as it arrives at Saturn after a journey from Earth of 4 years and 1 billion miles. The planet's rings are targeted for special study. They present the first of many surprises. In this hypothetical sequence, we may observe the changing appearance of the Saturn rings. All the great classic rings appear to break up into hundreds of small rings, and each of the narrow rings appears to be filled with yet narrower structures. Voyager 2's flight path allows scientists to make a unique study of the rings. A light-sensing instrument is pointed through the rings at the star Delta Scorpii, more than 587 light-years away. The amount of starlight passing through the rings is measured. The experiment finds that what appears to be hundreds of rings are waves in a sheet of icy particles with only a few gaps. The rings hold yet another surprise: dark streaks that orbit with Saturn and then vanish. They are clouds of dust suspended above the ring by some unknown method. Attention is shifted from the rings toward the known moons of Saturn. Mimas is the innermost of the larger Saturn moons, with an enormous crater, 80 miles wide and 6 miles deep. Mimas is thought to be frozen solid. Tethys, a moon scarred by a crater large enough to hold Mimas. And an ancient chasm more than 1,500 miles long. Dione, a moon with bright radiating patterns on one hemisphere and an underlying presence of craters. Rhea shows an icy face to the cameras. Bright streaks are probably fresh ice ejected from beneath its crust. Enceladus, an extremely bright moon that reflects more than 90% of the sunlight that falls on great plains of ice. A closer photograph reveals that it may be a recently active moon with internal heat that melted the surface. Iapetus, the outermost of the larger moons. The dark side contrasts sharply with the lighter trailing hemisphere, an oddity for which there is no present explanation. And Hyperion, an apparent fragment from the shattering of a larger moon, tumbling erratically in its orbit. The most intriguing of Saturn's moons is Titan, larger than the planet Mercury. It is the only moon known to have an atmosphere. Nitrogen and methane gases shroud Titan with dense clouds which our cameras cannot penetrate. The chemistry of this atmosphere is unlike that of any other. If we could descend to the surface of Titan, we might see ice mountains softly eroded by a persistent rain of complex chemicals, and a deep chemical ocean, a strange parody of the oceans of Earth. Titan's atmosphere, like the ancient atmosphere of Earth, contains pre-life chemicals, but is too cold for life to evolve. The moons of Saturn have a direct influence on Saturn's rings. A natural tendency of ring material is to spread both toward and away from the planet. But the moons, in a complex interplay of gravitational forces, shape the rings and define their structure. Jupiter and Saturn have not yet cooled off. Consequently, both planets give off more energy than they receive from the sun. And this energy is thought to be the heat engine that yields the stormy patterns of their intricate weather systems. An experiment has been performed which demonstrates how these weather systems could work. The major planets can be regarded essentially as rotating fluid spheres, which are heated from within. In the laboratory, this is simulated by a rotating sphere assembly. When instability is induced, long, thin columns are formed in a series of ever larger shells or layers. The layers create wind flows moving at different speeds, and the tips of the columns form the familiar bands of Jupiter's clouds. If this is what happens, and there are competing theories, it could change our understanding of weather systems on these giant planets. Jupiter and Saturn have dozens of storm systems. On Jupiter, the white opals are smaller versions of the Great Red Spot. The red spot is larger than several Earths and rotates in 6 days. This violent storm has existed for at least 300 years. Its center is quiet, but the outer rim seizes clouds and smaller storms and whips them around the edge of the spot. A series of blue filter photographs assembled to form a movie of the red spot enabled scientists for the first time in centuries of observation to study the storm's motion in detail. Saturn's atmosphere appears similar to Jupiter's, with alternating dark belts and bright zones, alive with eddies that swirl and dissipate their energy into atmospheric circulation.
In January of 1986, Voyager 2 approached the Uranian system after a 9-year, 1.8 billion mile journey through our solar system. Voyager 2 had come out of cosmic hibernation to explore Uranus, the 7th planet from our sun. In the next 10 hours, we would learn more about Uranus from Voyager 2's radio transmissions than we had in the previous 200 years of scientific study from Earth, including the discovery of 10 new moons and 3 more Uranian rings. Uranus had remained totally hidden until its discovery by William Herschel in 1781. Herschel was mapping the stars with his newly developed telescope when he spied an eerie, pale blue planet like no other in our solar system. Uranus's unusual color results from the absorption of red light by a high concentration of methane gas in its deep, cold, and remarkably clear atmosphere. This false color Voyager picture shows a discrete cloud seen as a bright streak at the upper right of the planet. The cloud's discovery was made possible by a series of Voyager images shuttered through violet, blue, and orange filters. Each of these color images shows the cloud to a different degree. In a true color image, the cloud would be barely discernible. The darker shadings at the upper right of the planet correspond to its day-night boundary. Beyond this boundary lies the hidden northern hemisphere, which remains in total darkness as the planet rotates. This is caused because Uranus, unlike any other planet, does not rotate about its poles, but rather on its side. This means that its southern pole always faces the sun, and its northern pole always faces away. Many scientists believe that a speeding cosmic bullet about the size of Earth struck Uranus and caused it to tilt over. Using Earth as an example, the Uranian southern pole would be approximately where Los Angeles is, and the northern pole would be in the Indian Ocean off the coast of Madagascar. Another strange discovery by Voyager 2 was that Uranus's hidden northern pole is actually warmer than the South Pole. This oddity is caused by some unknown internal heating process. Uranus does not exhibit any seasonal characteristics. Its temperature only fluctuates 3 degrees about its average surface temperature of minus 350 degrees Fahrenheit. Its rotation is extremely fast. 1 Uranian day is equivalent to 16 hours on Earth. This ice-laden planet, which is 4 times the size of Earth, has a unique system of rings. In this false color image, showing all 9 rings, we can see the 3 newly discovered innermost rings near the bottom in faint off-white tones. The outermost and brightest ring is known as Epsilon. Uranus's rings contain much larger and distinctly different particles than had been seen in Saturn's rings. The Uranian rings contain particles that are 10 times larger, measuring a meter or more in diameter than Saturn's marble-sized particles. Uranus's rings, blacker than coal dust, are one of the true wonders of space. Unlike the wide, symmetrical bracelets of icy particles circling Saturn, these rings are warped, tilted, and bizarrely elliptical and can vary in width by many miles. Uranus's gravitational pull, which was used to redirect Voyager 2 towards its next encounter with Neptune, also brought the spacecraft very close to the 5 previously known Uranian moons. Voyager 2 made its closest encounter with any of the moons when it flew by Miranda at a distance of approximately 18,000 miles. This innermost large moon shows unusual chevron features in regions of distinctly grooved terrain. Some of these grooved patterns indicate cliffs up to 3 miles high, higher than the walls of the Grand Canyon. Titania is Uranus's largest moon, with a diameter of more than 1,000 miles. One of the most prominent features of this moon is a fault valley that stretches for hundreds of miles and is 50 miles wide. In this valley, the sunward-facing walls are very bright. While this is due partly to the lighting angle, the brightness also indicates the presence of a lighter material, possibly young frost deposits. Another of Titania's distinguishing features is a massive, ancient crater formed during a violent period in Uranian history. Ariel is a densely pitted moon with craters 3 to 6 miles across. Numerous valleys and faults crisscross its pockmarked terrain. It is uncertain whether these sinuous features have been formed by faulting or by the flow of fluids. Some of Ariel's largest valleys are partially filled with younger, less heavily cratered deposits, giving scientists clues to its early development. Umbriel is the darkest of all the Uranian moons. It's largely featureless, except for numerous overlapping craters. This mystery satellite has an unusual white polar cap. Scientists believe that this bright spot was created when a large meteorite struck Umbriel, piercing its black, coal-like surface and exposing white ice, which was thrown to the surface, much like a terrestrial volcano spews up lava. Oberon is the second largest satellite in the Uranian system. It shows evidence, like many of the other moons, of meteorite impacts that have pulverized the gray surface, exposing an underlying layer of ice. Oberon's most distinguishing feature is a great peak towering 3 miles high on its lower limb. The tremendous amount of data on the Uranian system, sent back by Voyager 2, will challenge the scientific team of the Jet Propulsion Laboratory for many years to come. Meanwhile, Voyager 2 will go back into hibernation for its 3.5-year journey to its next encounter, Neptune.
We join Voyager 2 on the final visit of its 12-year grand tour of the outer solar system, Neptune, the blue giant. Voyager has traveled over 7 billion kilometers to reach its final planet. From 4 million kilometers, we look down on Neptune, its large moon Triton, and its small distant moon Nereid. Soaring from our lofty perch, we descend to just in front of Voyager. The spacecraft camera pans left to Nereid, about which almost nothing is known. These are the best images Voyager will take of the moon. Nereid is so small that we must take animator's license, zooming in by a factor of 20 to reveal its features. As the observation concludes, we pan back to Neptune. At 4 times the size of Earth, and 30 times farther from the sun, the last gas giant is a cold, mysterious world. We begin uncovering its secrets by examining its upper atmosphere. Neptune may possess partial rings called ring arcs, the likes of which have never been seen before. We zoom in to study one arc in detail. Voyager's camera tracks the arc as it orbits Neptune. Observing how ring particles deflect incoming starlight is the most sensitive ring study technique known to man. The star Sigma Sagittarii provides the means to uncover the secrets of the incomplete rings. Occasionally, a ring arc blocks the starlight, revealing arc dimensions and internal structure. Usually, the arcs are in the wrong position. Undoubtedly, a few will come tantalizingly close. About an hour before closest approach, we pass immediately above the ring arc region. As Voyager makes the traverse, it measures and records multitudes of tiny ring particle impacts. Then, almost brushing Neptune, we skim over the planet's cloud tops, avoiding them by only the distance between Los Angeles and New York. The spacecraft rolls to realign its instruments. Then we turn our attention to Triton. Triton is equally as fascinating as Neptune. Roughly the size of our own moon, Triton is one of only 2 satellites in the solar system known to have its own atmosphere. In addition, it orbits backwards around Neptune. These features make Triton unique amongst all moons. Our highest resolution pictures of the surface of Triton are provided by this 12-image mosaic. We pass within 38,500 kilometers of the surface. Triton occults the sun and Earth, providing the opportunity to probe the moon's atmosphere and to measure its diameter. After rolling to the star Canopus, we take a departing wide-angle crescent shot of the sunlit south pole of Triton. The first grand tour has ended, but Voyager's legacy will continue as it ventures beyond the solar system into the vastness of interstellar space. There, having paced upon the heavens overhead, it hides its face amidst a crowd of stars.
This movie shows cloud patterns on Neptune as seen by the Voyager spacecraft over a 68-day period. The individual frames of the movie are views of the planet at 17-hour, 52-minute intervals. This interval approximates the Neptunian day. However, winds cause the atmosphere to rotate up to 3% slower near the equator and up to 10% faster near the South Pole. Therefore, near-equatorial features like the Great Dark Spot and the neighboring bright clouds drift to the left in the movie. Proceeding southward, features like the small bright scooter, the faint dark spot, and the bright polar cloud all drift to the right. The movie uses images from the orange filter of the narrow-angle camera. Colorization produces hues that match those seen by the human eye. This polar view shows cloud patterns on Neptune as photographed by the Voyager spacecraft. The frames are centered on the South Pole with latitudes displayed as circles. The effect is to illuminate the planet uniformly. Winds cause features near the equator like the Great Dark Spot to rotate slower. These features move counterclockwise. Faster-moving features, like the small bright scooter, move clockwise. Colorization produces hues that approximate those seen by the human eye.
Here we have a panoramic view of Triton as Voyager 2 passes at close range. In the next sequence of photos, taken as Voyager begins its traverse into outer space, we have turned and are now looking back at Triton from a distance of approximately 29,000 miles. Scientists from the Jet Propulsion Laboratory in Pasadena and the U.S. Geological Center in Flagstaff refer to the source of these black plumes as geysers. The apparent up and down repetitive photo sequence is the result of comparing shots from two positions of Voyager for better viewing. These eruptions appear to be similar to volcanic action here on Earth, but since this is an occurrence never seen before, we as yet have no proper name for them. We do know that they are caused by frozen nitrogen gas emitting from below the surface of Triton and carrying up with it dirt and dust, hence the black plumes. Volcanoes here on our Mother Earth planet, on the other hand, eject hot gas and lava, whereas geysers emit water or steam. Following these sequences, Voyager 2 leaves the solar system to follow Voyager 1 in its endless trek into the universe.